topic we're going to talk about is oscillating motion. So here's kind of a rundown of where we're at in the class. So think about the first semester stuff. What we talked about was these types of forces right here. We talked about these types of energy, and then we talked about acceleration, deceleration, constant velocity, and not moving. And all of those you could use with the kinematics equation, SUVAT. We can use SUVAT to solve that type of motion. Now, second semester, we're still going to talk about this stuff up here, gravity, potential energy, kinetic energy, work, etc. But we're going to add a couple of new forces in there, centripetal force and electrostatic force. We're going to add in electrical energy, but then we're also going to talk about two different types of motion, oscillating motion and circular motion. So today's topic is going to be about oscillating motion. Now, let's start with this. Oscillating motion and circular motion both have something in common. They're both periodic motion, which means that they repeat themselves, which means that they repeat themselves, which means that they repeat themselves. What does that mean? Well, think about something going in a circle. Something going in a circle is going to get back to where it started after a certain amount of time. So if I look at this ball, if I have it travel in a circle, at some point it's going to get back to where it started. And then it's going to start all over and get back to where it started and get back to where it started. So since its motion is repeating, we call that periodic. For a wave or oscillating motion, think about like a pendulum or something swinging back and forth. At some point, it starts here, it's going to go forward and back to where it started. A guitar string, it goes up and down, much quicker, much more frequently than the pendulum would, but it's going to get back to where it started. So both circular motion and oscillating motion are periodic in nature. So let's define that. We have two equations we can use to calculate period and frequency. So the first equation we can talk about is period. Period is labeled as capital T, which means it's the amount of time it takes for the object to get back to where it started. So lowercase t is just any generic time it takes for anything to happen. Like for SUVAT, we use lowercase t because it's just like how much time does it take to go from start to finish or between two distinct points of displacement or velocity. So that's just any interval time. But capital T is very specific. It's the amount of time it takes for the object to get back to where it started. And this is defined by the number of seconds it takes for one complete cycle. Frequency is very similar to that. It's how often something cycles per second. So with like a ball that's rotating, it's how quickly it rotates per second. If it's a wave, it's how quickly it oscillates per second. And if it's a sound wave, we detect that frequency with pitch. The higher the pitch, the higher the frequency. It's oscillating back and forth much quicker. Next thing is we have a chart here. So this chart is showing the wave nature of an oscillating object. So think about a pendulum. A pendulum is a pretty easy visual to think about. If I have a pendulum and I just leave it sit for a long time, it's going to do that. It's going to be like that. It's going to be a ball on a string, and it's just going to hang there. That pendulum is in equilibrium, meaning that all the forces acting on the pendulum are balanced. There is gravity pulling it down and tension pulling it up. Those two are balanced. It's in equilibrium. That's its natural position. I would never leave the room and come back and see the pendulum just like chilling like this. That'd be weird. That wouldn't happen. So what we see is the pendulum just hanging there. That's its equilibrium position. What happens is when we displace the pendulum from its equilibrium position, it gains potential energy. And then when I release it, it gains kinetic energy and momentum. So it's going to swing back and forth. It's going to have potential energy up here, and then when I let it go, it's going to convert to kinetic energy and momentum. And that momentum is going to be like, hey, that ball's moving really fast. It's going to want to keep on going, so it swings up here. But now it slows down because all of its kinetic energy converts to potential energy, so it turns around. So it just keeps oscillating until eventually the dissipated energy takes over and it gets back to that position again. So we can get a graph that looks like this, up, down, up, down, up, down, up, down, and go from there. So let's label some stuff on the graph. Let's see. So there's two things that I want to label on this graph. First thing is I'm going to label the amplitude. The amplitude is the height of the graph. It's like the maximum displacement from equilibrium. So if this is the equilibrium position, the pendulum went up and down, up, down, where it went left to the equilibrium, right to the equilibrium, left and right, the equilibrium would be at 0. So the amplitude is basically the height of the graph. It could be that, or it could be that. And amplitude is, you'd think it'd be capital A, and sometimes it's used as capital A, but we label amplitude as x0. Initial stretch distance, initial displacement. Remember x, like elastic energy, was like how much it stretched? Well, x0 is just like the initial stretch, the maximum stretch. So this is the maximum stretch, or we can just simplify it as amplitude. And it's measured in meters. Then we can also measure something called the wavelength. The wavelength is the distance from one wave to the next. Now a wave is like the smallest section of the graph that you can actually take and repeat. So if I start here, look at that starting point, I go up a hill, back to where I started. But if I just repeated this section, I would just get a bunch of hills like this. That's not quite the full story. If I started here and went all the way to here, now I have a hill and a valley. If I repeated this, I would get another hill and a valley, another hill and a valley, another hill and a valley, etc. So a wavelength has to have a hill and a valley. So it's a distance from one point to the next. Now I don't need to start at equilibrium. I could start somewhere else. And actually I'm going to label somewhere else on this graph because it's easier to see. What if I started here at this point on the top? Where would my wavelength end? Well, if I started here, and if I went down to here, I can't repeat that. Like, if I repeated that, it would be like a mess. It would be like this. That's not a wave. But if I continued on this graph until I got back to where I started up here. When I get back to the top there, that's one wave. It repeats, because if I repeat this, I essentially have that. I get that again. So the distance from here to here is called the wavelength. And we abbreviate wavelength with a certain symbol. That symbol. It looks like an upside down Y. It's actually the Greek letter lambda. It's like the Greek L. Because regular L is used for length. So this is a very specific type of length. So we went with the Greek letter wavelength, lambda. So this is wavelength, which by definition is the length of one wave. So we can write another equation for wavelength. Wavelength equals the length of whatever's making the wave divided by the number of waves. So it's defined by the whole length of whatever's making the wave divided by the number of waves. So think about it like this. Let's say the distance from here to here was 1 meter. The distance from here to here was 1 meter. What's my wavelength? Well, if I did that calculation using this, my wavelength would be 1 meter divided by the number of waves. So now let's count the waves. Let's count how many waves there are. There's more than one wave there. So if I start here, I have one wave right there, two waves right there, and then I have, not quite a full wave there. It's actually half of a wave. It's 2.5 waves. You see that? So one wave energy right here, two waves right here, and then I get another hill, not a valley. So I get 2.5 waves, 2.5 waves. So the length of one wave is less than 1. You can see it's obviously less than 1 meter. Because 1 meter is this length, it's less than 1. So it'll be 1 over 2.5, which I believe is 0.4. Yes. So the wavelength is 0.4 meters. So this is another equation we can use. Now, a fourth equation we can talk about with waves is speed, wave speed. Think about like Suvat, we talked about acceleration, velocity, time, initial velocity, displacement. Well, we already kind of defined displacement. Displacement could either be amplitude or wavelength. We talked about time. It can be period, and the inverse of that is frequency. So we have that. With waves, there's no acceleration. So that's nice. It's a constant speed. So the last thing we have to figure out is speed. How do we find out speed? So speed or velocity is equal to, well, think about average speed. It's distance over time. So this is not the equation we want to write down. Distance over time. What we want to do is actually write it in terms of wavelengths and frequency and period. So what's the distance that a wave travels? Well, the shortest distance a wave can travel is the wavelength. And in that wavelength, if I want to figure out how long it takes for one wave to happen, that's the period. So velocity can be wavelength over period. More commonly, that works, but a more common way to write speed is because these are just inverses of each other, seconds per cycle and cycles per second. A more common way to write velocity is wavelengths. Instead of dividing by period, we multiply by frequency. It's the same exact thing. Because frequency is 1 over period. So just basically taking 1 over t, put an f in there instead. So then you don't have to divide, you can just simply multiply. So that's a more common equation. So let's say, we'll do a couple of examples here of period, frequency, and wavelengths. Last thing we're going to talk about with standing waves is harmonics. Harmonics are basically just different types of waves you can produce in a system. So think about like a slinky here. I have a slinky. I want to make a wave. So the very easiest way that I can make is something like this. All right. I can't make a wave that does this. I mean, I could, but it's not very stable. So harmonic is a stable wave. It's a standing wave, meaning like the nodes, the points the equilibrium points don't move, and the middle point moves. That's a stable wave. It's a standing wave. It's very stable. The next one I can make with this slinky that's stable is if I have two hills. It's hard to do with a single person here. Actually, I have a wave generator, which can actually do it better for me. Okay, so you can kind of see it a little bit. So I want to make the first harmonic here. You can see the first harmonic there is essentially, see the first harmonic there is essentially just a peak in the middle and nodes at the outside. So then if I put my finger in the middle, I can see there's two hills here. I'm going to shorten it a little bit. So there's a much better way to see it. So that's the second harmonic. Third one is if I have something like this, where there's three peaks. And then obviously the fourth harmonic would be something with four peaks. So let's do a sample calculation with a little demonstration here of like how do we calculate the speed of like a wave or something. So what I'm going to do is I'm going to produce a wave here. That's the first harmonic. Okay, let's do then get the next one. This next harmonic. Let's see if I can get the third one. There we go. Kinda. There we go. So, here's some measurements that I need to make. I'm going to use that third harmonic. So, the distance from here to there is 1 meter. So I'm going to draw that out. That third harmonic. So I usually draw the dots at the equilibrium point. The distance from there to there is 1 meter. I want to figure out the speed of that slinky. What was the speed that the slinky was traveling? The speed of the wave. So, in order to figure out the speed of the wave, I need to use this equation right here. Wavelength times frequency. Well, I have one measurement there. Another measurement that I need to get is the frequency. Now how do I get frequency? I need to get cycles per second. So let's look at that closely here. Okay, I slowed this video clip down as I got that third harmonic. So what I need to do is I need to count how many cycles it goes through in a certain amount of time. So let's start right now. 1, 2, 3, 4, 5. So just to verify, just to show you exactly how I counted those. It was kind of wonky. It's hard to do it by yourself. But what I did is like every single time it got back to this middle peak, got back to the top, that was another cycle. So I did 1, then it went down and up. That was 2, down and up. That was 3, down and up. So it's 5 cycles. 5 cycles, and the video was slowed down. The original length of that video was 3 seconds of what I originally timed. So 5 cycles in 3 seconds. So we can actually go through now and calculate all 4 of these things with the wave. Let's start with the period. What is the amount of time it takes for that wave to go up and down? That's what the period is saying. Well, period is just seconds per cycle. So I just take seconds of 3 divided by 5, you get 0.6 seconds per cycle, or 0.6 seconds for short. So the period is 0.6 seconds. Perfect. What's my frequency? It's the opposite of that. It's cycles per second. So my frequency is 5/3, or 1.67 cycles per second. Another way to say cycles per second is hertz. Hertz means cycles per second. So it means it's going up and down a little over 1.5 times per second, 1.67 times in a second, which is why I need to slow the video down because I can't. It's hard to count that fast. The wavelength. Wavelength, once again, is defined by the length of one wave. So if I look at this, maybe the length from here to here. Oh shoot, how long is that? I want to find this length right here, which is less than a meter. So I can use this equation to help me. What I do is I take the total length of the slinky, which was 1 meter, and divide by the number of waves. How many waves do I have? Well, this is half of a wave, this is 1 wave, this is 1.5 waves, because there's another half there. So my wavelength is 1 meter divided by 1.5, which is 0.67 meters for each wave. Finally, what's the speed of my slinky? It wasn't moving super fast, but what I do to find the speed of my slinky is I take my wavelength times my frequency. So I take 1.67 times 0.67, and I get 1.12. And then that's just wavelength of 0.67 times frequency, 1.67, gives me just the velocity in meters per second, 1.12 meters per second. Look at that, those 4 equations help me. So I need to find period. Period, once again, is like how long does it take for one cycle to occur in seconds. Frequency is how many cycles does it do per second. Wavelength is how long is one wave in that cycle. The distance for one wave. And then the velocity, obviously, is how fast the wave's going. So those are our 4 equations for standing waves. Hopefully they make sense. And that's it for standing waves. Stay tuned for simple harmonic motion.